Good morning. We are at the beginning of page 88, which is the start of section 8.3 in our workbook. And this section is the continuation of the topic that you started studying in section 8.2, where you were talking about geometric series. Geometric series were series that had that special structure of having a common ratio that allowed us to determine pretty easily whether the series converges or not. Section 8.3 continues that and asks the question, how do we tell whether other series that aren't geometric converge or not? And what we'll do is in this section is to develop a variety of other tests that we can use to test other types of series for convergence. Okay, so let's get our discussion started by looking at example 1 here. Okay, it asks us, what is the value of the infinite sum from 1 to infinity of 1 over n cubed? Let's first remind ourselves of what that notation means. Okay, so we're basically starting from n equals 1. Okay, and we're counting up by whole numbers. So if we plugged our first index in, we would get 1 over 1 cubed. Then we'd move on to n equals 2 and get 1 over 2 cubed and just keep going. And that's what the terms in our sum look like. If we write out the actual values, we'd get 1 over 1 plus 1 over 8, because 8 is 2 cubed, plus 1 over 27, and so on. Okay, and so our infinite sum of numbers looks like that. Okay, well, how do we decide whether this series converges or not? Well, one way is to look at what's known as the partial sums of the series. Okay, partial sums just mean that we're gonna add up more and more terms and look at those sums and try to decide whether they're approaching a number or maybe going off to infinity. So we'll start with what we're going to call S1. That notation just means the sum of the first term in the series. Okay, so we're just going to take 1 over 1, that was our first term, and that's it. That's the first term in our series. S2 would be the sum of the first two terms, so we'd be taking 1 plus 1 over 8. Okay, we can actually do that addition. That's 9 over 8 if you add those fractions. Or as a decimal, that's 1.125. There's the sum of the first two terms. Okay, sum of the first three terms, same thing. This time we're just going to go up and stop when we reach that third term. Okay, and there, if you get a decimal for that, that's about 1.16204. And the question is, what's happening to these numbers? 1.125, 1.16204, are they approaching something or going off to infinity? Okay, well, that's not so clear just looking at the first few terms. So what I'd like to do now is to go to look at partial sums a little bit farther out. Okay, this would be difficult to do by hand. For example, S20, the sum of the first 20 terms. So I went to Mathematica and actually had it add up the first 20 terms for me. And here's what it came up with. Okay, and then I had it also add up the first 40 terms. Okay, and then the first 80 terms. Okay, and we can look at those numbers and ask, does it look like we're approaching something, or are we maybe going off to infinity? Okay, and the thing that I'd call your attention to is if you look at these last two, if you were to round off to, say, 3 decimal places, both of those numbers round to 1.202. So we could maybe make a conjecture here that it looks like this series is converging to about 1.202. Okay, and you'll notice that I underlined the word appears. This is really just a guess at this point. Okay, we're looking at the data and making an educated guess that this series converges. We can't really be sure about that yet. Okay, so the goal of this section as we go further will be to find a way to be sure that this really does converge. Okay, that will come later though. So for now, let's take a minute to just scroll to the bottom of the page here. Okay, and we are going to formally define what we mean by an infinite series, just kind of using the idea that we developed in the above example. Okay, so an infinite series, just like it was in the previous example, is an infinite sum of numbers. Okay, and to determine convergence, we're going to look at the sequence of partial sums. That's the same idea that we used above. Okay, so Sn just represents the sum of the first n terms of our series, and the sum of the entire series is just going to be the limit of that sequence of partial sums. If we wrote that out, it just looks like this. This is that process of just taking more and more terms, adding them up, and then asking, are those sums approaching anything? Okay, we could also write this in sigma notation like this. Okay, and then just one last word to go with this definition. If it turns out that these partial sums approach something, then we'll use the word convergence. Okay, we'll say that the series converges to the number